Yeah, on YouTube. Got a terrible hangover. However, some of you are talking about stuff like talent, and when it comes to computer engineering, you don't need that much talent. What you rather need is factual knowledge. And so if you want to get started in a certain topic, like in microcontrollers, then the one thing that is really important, the way I started, is by reading the datasheet. Especially the AVR controllers, the Atmel controllers, have great datasheets, detailed and I'd say high quality datasheets. The datasheet of a typical Atmel controller, not the short version, the long version, is more like, it's more like a book. It has, this is the ATmega 88 datasheet. Since the only difference between those two controllers is the memory, the rest is identical, and they are pin compatible. So this is one datasheet for two controllers actually. It has 378 pages, which for me is more like a book than it is a datasheet. But you have everything you need right in here. And there are code examples in the datasheet. I mean, people probably don't even know that, but there are lots of tutorials and stuff around out there, but this is from the source, and typically you can trust the source much more than you can trust another party, some tutorial or whatever. Good tutorials out there, but especially if you start with this stuff, you never know. Yeah, you're not so versed in this as to realize there is some crap in those tutorials. And this can cost you a lot of time and nerves. I mean, how does a microcontroller work anyway? Well, you need to know, the most important part of the datasheet, if you really start, is this, the block diagram. And this is the block diagram. Oh yeah, that's a small one. Is this the whole block diagram? Let me see. Yes, it's a small controller. So the block diagram of this controller shows you what it consists of. What a microcontroller always has is of course a CPU, but as you can see, it has SRAM, which is the main memory. I mean, you need to understand that especially AVR controllers and many other controllers are Harvard RISC based rather than von Neumann based, which is the architecture in a typical computer. What is the difference between those two? The difference is that in a Harvard RISC architecture there are separate program spaces for data and for program instructions. I mean, the program is stored in another memory. Then is the data of your program. This sounds simple, but it has a lot of consequences. Because the flash, that is the program memory, while the SRAM here, that's the data memory, and you can't just interchange those two. On a computer, your program is loaded into your main memory, and this is one memory, and it also holds the data and the instructions, which means the instruction pointer of an AVR CPU will always point in here, never in here, which means you cannot just store executable code right here. And you have a problem if you try to store, say, data, program data here. Although there is a trick with the AVR controllers, in the Clip-C controller, where you can at least store string constants and some stuff in the flash memory. But you need to do this, of course, when you program the controller. But let's not get too far away here. It has an internal data bus, and that connects the CPU and the memory to the rest of the system, which is mainly then peripheral units. It has an EEPROM. This is something you can, as you can see here, read and write from the CPU. This is a little strange here. It says here bidirectional. This isn't exactly. Yeah, it is true, because if you have the CPU in a special mode, you can do both, but in normal program operations this doesn't work. You see, that's exactly what I mean. This is an example. I says to myself, wait a minute, yeah, this is all very detailed stuff, and the details do matter. It has a power unit with a brownout detector. This is what BOT stands for, brownout detector, and the reset unit. Debug wire and program logic. This means that you can, this is a very sparsely debug interface you can use on this controller. For such a small controller, that's good, because it doesn't have a JTAG interface. This controller is just too small for a JTAG interface. And then it has one thing that is, of course, very, 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 very important, and this is the timer. Oscillator circuits and clock generation, and then you have a watchdog timer. Where is the normal timer in here? Clock generation, watchdog oscillator, and watchdog timer. No, this is the timer. 8-bit timer and counter. Timer and counter. TC stands for timer and counter, and it has a 16-bit timer and counter, which has a much better resolution, and the counters in a microcontroller are very, 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 very important. If you have typical application without a timer, probably never. It has an AD converter, and those are all peripheral units here, all peripheral units. And what, of course, is very, very, very important for a controller is the general I/O. It has not so many I/Os, 3 ports. A port in a controller, if this is an 8-bit architecture, always is, of course, is 8 bits large, 8 bits wide. If you have a 16-bit controller, a port will be 16 bits wide, and so on. Because that corresponds with the register length, and those ports are written over registers. That's something you cannot see right here because it's just a block diagram. It gives you an overview of what a microcontroller is. It has an SPI unit. This is something that is directly connected here to the ports, but not so directly as to can use a port both ways. You see this one? It goes right here, like this and like this. This means the user, for example, this is the serial transmitter, can be connected to port D, but it must not be connected to port D. So you can use all ports as general I/O pins, or you can have the peripheral units behind it, the SPI, or this is the 2-wire interface. So now a comparator is something you don't need so often, but because you have an AD converter, but this is connected to the AD converter. Some should it? Yeah, internal bank analysis is connected to the both, because the AD converter needs the analog comparator, but you as a programmer probably won't need it. You probably use the AD converter directly. This is probably why they have another color here. You see, I don't even know what about some of the conventions here mean. A thing like that, with this 2 here, this thing, this means this is 2 bits wide, and this means this is 6 bits wide. This bus connection here, that's what it means. Yeah, now this is the controller, and in the data sheet, of course, well, interrupt logic you can see here. The interrupt logic is probably part of the AVR CPU core, and this is why it isn't just somewhere here. If you start That's a problem with this shit here. If you start, you should begin here, I/O ports. And in this chapter 11 here, the I/O ports are explained. And as you can see, it's very detailed. And this is a lot of text. Okay, but if you start out, you just read this. It's like a book. And here it says ports is general digital I/O. And then there's probably the next thing says special operations or something like that. Here, this for example is a code example of how to do I/O operations. It's not only in assembler but also in C, the equivalent C. And with this you can always start. And from this you can modify your code and look what you can do different for your own program. Digital input enable sleep mode, unconnected pins, alternate. Here it is, alternate port functions, which means if you use an I/O port with, as I just explained, with one of those other units like the 2i interface or the serial transmitter, then it's an alternate port function. And it's also explained how you use it. There's probably somewhere in here also code. Well, so I mean, this doesn't need much code. Yeah, that's the next thing that is very important, and the datasheet is full of it. Register descriptions. This is the MCU control register. You need to know that most of the operations in a microcontroller are configured over registers, read from registers, written to registers. So what you do on a microcontroller is mainly read and write registers all the time. And every bit in this is a register. A register is on an 8-bit controller, 8 bits long. 0, this is the least significant, the most significant. And those bits are not used, for example. And here it says whether you can read and write. And this is bit based. I mean, this is a little funny. There are registers where only a few bits can actually be written, and others can only be read. I mean, those which are not used, for example, cannot be written. And you can write it, but it will always read 0. And it says here initial value. This is also very important because after you start up your controller, it's always initialized, all registers are initialized with this sequence here. And this is not always, most of the time it's 0, but not always. And for example, I'll give you an example how you do digital I/O. For example, there's a port A, there is no port A, port B. This is the port B data register, the direction register, and the pin register. Those 3 registers are used to do digital I/O on a controller, standard digital I/O, like you want to let your LED blink. So what you need to do is the direction register initialized with 0, which means in that case, if one of them is written to 0, those are all inputs. Now if you want to, for example, DDB4, that's the pin, as an output, you need first write a 1 into this bit of the port register, then it is an output. And now you have the pin register, which has a very interesting operation, because it depends whether you have an input or whether you have an output. For example, if you have an input and you write a 1 into the field of this register, then it means that it activates the internal pull-up, for example. So no, sorry. That's bullshit what I just said. The pin register. is used to read the port. This is why it says only read. You can use it to read the value of a port if the direction register says that this is also an input. Funny thing on the Atmel controller, for example, is you can always read the pin B even if it is an output, and then it reads back the value that is currently output. Yeah. Yeah. That's just about how digital I/O operations work on a controller like this. You have the direction register, which specifies whether this is an input or an output for every pin on the register. Port equals to the register. This is also, of course, why a port is an 8-bit architecture is 8 bits wide. And this is a simple reason, because it is one register length. Everything else would be quite crummy. Funny thing, although, is on the physical pins of the controller, this mustn't be just, can be where it is on the controller. I mean, sometimes you have one bit of the register here and one bit on the other side. That is not so luckily if you do your layout, but that's how it is. A port, this is where you will write your output data to, for example. You set with the direction register your port to output, and this is where you write. This is where you would write the data to into the port register, and this is where you read your input data. Port is used for writing to the register. Pin is used to read from the register. Yeah. And the direction register is used to set the direction. Yeah, this is it. And of course you can get very deeply into this stuff, and you need to. For example, the timer interface. The timers say the 16-bit timer is very elaborate on such a controller, but it's very powerful as well. If you see the block diagram of the counter, you probably realize that the 16-bit counter is a little bit complicated. But because it has so many different modes and stuff, this is something that took me a while to understand. Let's just say it like that. It's probably the part that might take you a little while to understand, but it is very, very, very important to understand the counter. Without understanding the counters of this controller, don't even start. Okay, maybe you have some pointers now. You want to get hooked on this stuff. It's also one of the problems. You can get hooked on this stuff once you start. It doesn't leave you alone. So be warned, this might be the case. Okay, I hope this was a little helpful in getting you some pointers, and yeah, have a nice day and see you soon.